are always nice, so I'll go ahead and run through my own PowerPoint with you and just kind of talk to you about what they need to know and how you need to, what you need to know and how you need to present it. So you got your title slide. So the first thing that we want to do when we're talking about any kind of performance charts dealing with ground effect is we need to define ground effect itself. So you need to have a slide in here that talks about this, and it's kind of a nice refresher back from one of the first ground lessons that you'll be going through with your students on aerodynamics. So what ground effect is, as you can see, it's an aerodynamic phenomenon which gives you increased performance when you're hovering within one rotor diameter of the ground. So the reason why we have increased performance is when we're hovering within that altitude range, we have a reduction of induced flow. Now, they should kind of remember from their aerodynamics ground lesson that there's two components of the relative wind. There's induced flow and there's the rotational relative wind, or you can kind of think of that as horizontal airflow. Anytime we have an increase in induced flow, we naturally have a drop in angle of attack, which decreases our overall performance and vice versa. So getting into defining our terms here, when we're talking about in-ground effect, when we are hovering within one rotor diameter of the ground, we have ground effect, we have that aerodynamic phenomenon. Now, OGE, or out of ground effect, we are high enough to the point where we are not getting that added benefit from the ground itself and its ability to reduce induced flow throughout the rotor system and therefore give us an increase in angle of attack. Now, the entire point of your IGE and OGE charts is to try and give you the altitudes at which, or temperatures or weights, that you would be able to perform either an in-ground effect or an out-of-ground effect hover, depending on a couple of different variables, which we'll discuss here pretty shortly. So now, just a little bit of basic information that you need to know or that you need to mention before you get into the charts themselves. These are designed, and I want you to remember this for later, they're designed to show the allowable gross weight with pressure, altitude, and some kind of temperature combination. That's the way they are designed, and they are required to be designed by the FAA for every manufacturer. So this is something universal. When you go fly an A-Star, you go fly a Bell 206, you get out the POH and you look up their performance charts, they're all going to be designed in a similar manner. Now, for the R22 and the R44, they were tested in Big Bear, California back in the 70s under quote-unquote ideal conditions. All that really means, it's just a statement that tells you that the aircraft's performance is going to vary, okay? And we'll talk a little bit later about the factors that are going to influence that, but all that really means is that conditions may vary. So it's giving you an educated guess at best. All of these were tested with carb heat off, okay? The charts that we're going to cover today are for the R22, and they're the same thing, or they're extremely similar for the R44, and a lot of these concepts are going to apply to both, okay? But for the charts that we're looking at today, the carb heat was off. However, with full carb heat applied, you can take a max of 2,000 feet off of whatever performance estimate that you get from your charts. So it's also something your students need to know, and it's something that they need to factor in when they are filling out cross-country information for a stage check or just any cross-country in general. So let's kind of get into the basic parts of it. So again, tested in Big Bear, California, full throttle, 2-foot hover, 0 wind, max RPM at 104%, and it's up to 9,800 foot density altitude, okay? So those are your conditions. Now, this yellow portion of the chart that you're looking at here, this was the conditions in which the aircraft was originally tested, okay? So make and model, engine type. Now, everything that you're seeing in the highlighted green here, this is an FAA authorized extrapolation. Okay, I know the little thing right here says interpolation, but it was actually extrapolated. Now that may be something that I doubt that an examiner would be too picky about, but technically the correct term is that it was mathematically extrapolated. Extrapolation and interpolation are two very different things. So what we basically need to take away from it is that this area here, again highlighted in green, was not actually physically tested by a test pilot in an aircraft. This is a mathematical calculation based off of the data here highlighted in the yellow. Okay, so that may be an important point that you need to kind of point out to them that an examiner might want to hear or might be a little bit picky about. So now the parts are kind of continuing on with the parts of the chart. On the left side, or you can consider this your y-axis, you've got pressure altitude in thousands of feet. It starts at 5,000, goes up to 14. Down here on the bottom, or your x-axis, you have the weight in pounds. It's going from 1,100 to 1,400 pounds. Okay, now if you look right here for the R22, it's annotated that the gross weight ends at 1,370. Okay, that is that big black bold line that goes vertical here, and it lines up roughly where 1,370 would be on your weight axis. Okay, now you have a temperature scale in degrees Celsius that runs to the right of that line, so it goes from 40 to negative 20 degrees. Now right here along this red line that was just highlighted, this is where the FAA told Robinson you cannot extrapolate this information farther than this. So this actually goes out to 12,600 feet density altitude. So with these temperature and altitude combinations, if you took out an E6B or a CX2 and you actually plugged those into your calculator, you would see that you would get approximately 12,600 feet. That's what this line represents, okay? All right, so using the chart, again, the way that these were actually designed to be used is reading it from your pressure altitude over here, you read it over to a temperature, you go straight down, and that gives you an ideal weight as that you would need to actually pull this off. Okay, now keep in mind that we're talking about in-ground effect here. So this is when we're hovering within one rotor diameter of the ground. Okay, so let's kind of go through an example. So you need to land at an airport that's roughly 9,000 feet pressure altitude. Your OAT is 10 degrees. Okay, so you take it from 9 here, we go straight over into where it intersects the corresponding temperature line. In this case, it's 10 degrees. You can kind of see that right there. You go straight down, and that's the maximum weight that you would be able to in-ground effect hover with here. Now, I stress in-ground effect hover. Just because you can't in-ground effect hover somewhere does not necessarily mean that you cannot land. Okay, that's going to get into a little bit of those factors that are going to affect this, which we will cover here coming up. Okay, so now that's not the only way that you can read this chart. It is how it's designed and intended to be read, but you can read it different ways. Okay, now if I am not capable of changing how much weight that I have, okay, in a scenario where I have to take a certain amount of fuel, I can read it from a weight up to a forecasted temperature, and that will tell me whether or not I will be able to land at one airport versus another based on the altitude at which they're at. Okay, so let's say they were at 1,300 pounds, the OAT is 0 degrees. So we start at 1,300 pounds, you go straight up to the corresponding 0 degree line, which is right here. Take it straight over, and that's going to give you approximately 10,500 feet. So that pressure altitude is the altitude in which you would be able to in-ground effect hover that altitude and below. Now again, if we need to land somewhere, let's say there's a hypothetical airport within the continental US at 11,000 feet, that doesn't exist. The highest airport in the US is roughly 9,000 feet, Colorado. But for argument's sake, if there was one at 11,000 feet, we would not be able to in-ground effect hover there. Now again, that doesn't mean you cannot land there. You could do a running landing. If you had wind, keep in mind this was 0 knots of wind, so if I had 30 knots of headwind down the runway, I probably could in-ground effect hover, among some other various factors that could affect it. Those are two of the biggest ones. Okay. All right, now this is kind of another common thread that students typically have problems with when they go to a stage check. They don't understand what extending the lines mean. They don't understand why we do it, and they really don't know how to apply it to a scenario. So let's talk really briefly about that. So you'll notice that these lines stop again at 12,600 feet. Now that begs the question, okay, what if I have a condition to where I'm at 1250 pounds and it's about 40 degrees? I go up and there's no temperature line there. So what do? Well, you can extend the lines, and that's kind of what it would look like here. So the important thing that we need to teach and that the student needs to realize is that when we extend these lines, we're only extending them up to a pressure altitude that would require a limitation, and that limitation being your 14,000 foot density altitude rule. You also got to keep in mind, this isn't an R44 chart, but you also got to keep in mind your 9,000 foot density or altitude, AGL altitude rule for the R44, excuse me. So you can extend these lines up to 14,000 feet density altitude. Now, if the R22 was actually limited to 15,000 feet density altitude, then we could extend it to 15, so on and so forth. You can extend these lines, as high as you want, but eventually you're going to reach a limiting density altitude, okay? And that's per section 2 of our POH. That's what they need to understand. So yes, we can extend these lines should we find a reason to. You're going to be hard pressed to find a reason to in reality, but hypothetically, yes, we could extend these lines, but you are going to have a corresponding limitation eventually that you will not be able to go above per section 2 of the POH, okay? Now, another thing that they need to understand is that it's much safer to just take the lines over at 12,600 foot DA, okay? What that's going to do is it's going to give you a slight buffer between that and your limitation at 14, okay? The higher up as far as density altitude that you're flying in, your risk factor is also correspondingly going to go up. And that's something that they need to understand. So just to kind of give you a brief example of what that would look like, if I just, I didn't extend the lines, I just took them straight over here. You can kind of see with these green lines that are annotated on the slide. That should give you a safety buffer that will keep you away from being close to exceeding that limitation, okay? You also got to keep in mind too, if I have an engine failure at 14,000 foot DA, the rotors are going to stall at approximately 94%. So 80% plus 1% for every 1,000 foot of DA is the rotor RPM at which you would stall should you get that kind of an RPM drop. So it's another important point that you want to make. So let's say that we're at 1275 on our weight and it's 40 degrees Celsius. So right here, if I just stop, I don't extend this to 14,000 feet. If I just go straight over from where the chart stops at 12,600 feet, that's going to give me an in-ground effect hover ceiling of approximately 8,200 feet. Now, you can see on your DA calculation here, it's roughly 12,680 feet, which matches up with our line, okay, approximately. Now, if I extend them, that puts me at 13,993. So you're 7 feet off from breaking a limitation, okay? So there's a pretty big difference between those two. So that could be, it could theoretically be the deciding factor as far as whether or not you stall should you have some kind of an engine failure. Regardless of the engine failure though, your performance is gonna be pretty horrendous and it's not gonna be safe up there to fly anyway. And 12,680 foot DA would be a nightmare as is. Okay, you need to take some notes of these. Your factors affecting your in-ground effect height. Your winds are definitely going to affect that. I'm going to be able to, I could probably hover at any altitude I wanted to if I had 100 knots of wind, okay? If your surface is anything but smooth, it's going to decrease your in-ground effect hover. So trying to hover over water, grass, anything except smooth concrete, that altitude is automatically going to go down. Your chart does not take that into consideration. If you remember from the top little label, everything was demonstrated when they tested that over a smooth hard surface. Any kind of obstacles, you're going to get some obstacle-induced recirculation. You can read a little bit about that in the Principles of Helicopter Flight. It actually has a really good section on it. Density, altitude, pressure, altitude, weight, those are all factored in on your chart, so that wouldn't be something that I would necessarily have them write down in their books or in their POH, but just double checking that they understand it. Humidity is going to mess with it. Blade cleanliness is going to really screw with it. If you have dirty blades, it can decrease your performance up to 1.5 inches. You also got to kind of take into consideration the condition of your aircraft. So if you're flying an aircraft that's getting close to overhaul versus one that just popped out of the factory, you can kind of do, common sense is going to tell you which one is going to be able to hover higher. So carb beat is also going to reduce it as well. All right, let's get into your OGE charts. So the difference between these two is it shows you, okay, just some differences to point out here. You're going to have a full throttle line here, which we'll demonstrate here in a minute. Those are your testing conditions, make and model. Now, these two don't really change. You still got weight, you still got pressure, altitude, density, altitude, 12,600 feet. It's the same mathematical extrapolation. Now, the big difference that you're going to see here is that we actually have a full throttle line. Okay, now everything to the left and down of your full throttle line, this green area here, this represents takeoff power, which in the case of an R22, that's your 5-minute takeoff power where the engine is producing 131 brake horsepower. So what you need to take away from this is that if I want to do an out of ground effect hover at 1,350 pounds and 40 degrees, you know, if I'm up here at about 3,800 feet, it's going to take my 5-minute takeoff power to do it. Okay. Now, when we get to full throttle here, this is the altitude beyond which I will not be able to get the engine to produce 131 brake horsepower anymore. Okay. They need to understand that. This is your full throttle line, and it also gives you corresponding temperatures, altitudes that you would reach full throttle per the temperature range. I'll go over that a little bit later. Okay. Not a limitation. Again, it's another performance chart. Okay. This is your out of ground effect at full throttle, shown here in highlighted blue. So everything after this dashed red line here, if you are going to perform an out of ground effect hover with these conditions, so 7,000 feet, 40 degrees, and 1,250 pounds in this case, you will be at full throttle when you are doing that, okay? Now, if you don't quite understand full throttle, or if you need a little additional instruction on that, you can talk to me. I have a pretty big Word document that I typed up over full throttle that'll help you understand that a little bit more. So we're gonna briefly cover that in this. If you need a little bit more help with it, you can get with me later on it. You do have a temperature conversion chart here from Celsius to Fahrenheit. Now, we're looking at the same principles as far as how to read the chart. You go from pressure, altitude to a temperature, and that gives you your weight that you would be able to out of ground effect hover at in this case, okay? Now, you can do the same thing. You can read it different ways. You can use an altitude and a weight to show you a temperature that would be required in order to hover. You can use a weight and a temperature to show you an altitude that you would be limited to, so on and so forth, okay? You can read this chart in different ways, but the student needs to understand that it's designed and meant to be read from pressure, altitude to temperature to allowable gross weight. Now, one thing that I'm really going to expect from a student if I'm doing their stage 3 or if I'm getting them ready for a check ride is that they need to understand that if I tell them, hey, I want you to go land on this mountain out here, this is one of the first charts that I expect them to get out, okay? Your in-ground effect charts are designed to show you what or where under what conditions you will be able to hover over a smooth hard surface. A mountain is not a smooth hard surface. We have to use this because it gives us a more accurate representation as far as how we're going to be limited landing off airport. This is something that people are going to expect when you go apply for a job doing tours, you know, whatever it is outside of outside of a flight school. Okay. So again, you got an example here. You can kind of use it both ways. We already kind of talked about this with your in-ground effect stuff, so you can kind of see your two different scenarios here in red and blue. So the first scenario, you want to hover at 6,000 foot pressure altitude, 40,000 degrees. You would not be able to do that above a weight of 1,300 pounds, okay? Now, the other example, you have to be at 1,350. There's no way that you can reduce your weight, and the temperature at your landing zone is 0 degrees Celsius. So start here at our weight, go up to our temperature line, and that tells us the altitude above which we would not be able to perform an out of ground effect hover, okay? Again, this is per the chart. Different conditions might allow you to do that higher, different conditions might allow you or might limit you to an even lower altitude, okay? This one's a really big one right here, 0 wind, okay? Now, same concept with extending the lines. You can extend the lines, but you cannot do it past 14,000 foot density altitude, okay? Again, it's safer to take the lines over at 12,600 DA. The student has to understand that. If you try to hover above these limits, it could give you low rotor, you could get yourself into vortex ring state, LTE, combination of all three, you know, if you're having a really bad day, okay? Still the same density altitude that the chart is stopped at, but again, this is something that they need to have drawn in their book, and they need to be able to explain why we have these. Okay, this is basically the same conversation that we just had for in-ground effect. It's always safer to take the lines over because it gives you a buffer, okay? Here's going through a couple of different scenarios. So your weight's 1,100 pounds, temps 30 degrees Celsius. With your extension, okay, with extending the lines here, you can see 1,100, okay, this temperature extension, that gives you a density altitude of 13,947, so you're pretty darn close. Without your extension, if we cut it off right here, where that little orange bubble popped up, take it straight over, 9,000 foot, okay? Density altitude is still pretty high, but it keeps you away from that 14,000 foot rule that we can't exceed. There's your difference. All right, so very briefly on full throttle, and this is a definition that I would expect somebody to be able to know, recite, as well as understand. So full throttle is the point at which the engine can no longer produce any additional horsepower. You can notice that the word additional is highlighted. In an R22, we have a lapse rate, if you will, of 7 brake horsepower for every 1,000 feet of altitude, okay? Your temperature and your altitude are going to influence the point at which the engine cannot produce any more horsepower, okay? Now you got to keep in mind, you know, we're in a helicopter right now. If you're in a car and you reach full throttle, that just means you can't go any faster. If we reach full throttle in a helicopter, it means that the engine cannot continue to produce enough thrust to turn our rotors at the pitch that we're trying to put it at with the collective. That's one way you can think about it, okay? Another thing that might help a student kind of understand what full throttle is if they're not like super technically inclined with an engine is the air is so thin that the engine cannot suck in enough air to continue to produce the horsepower that you need to keep your rotor spinning if you try to pull the collective. Now, if you keep pulling the collective after that, eventually you're going to get low rotor, and you're going to get the recognizing symptoms that we talk about all the time. Safety Notice 24 gives a pretty vivid description of what's going to happen should you let that get any worse. Okay, so let's look at some numbers here. So the R22, let's just kind of talk about a theoretical situation. If I were to walk out to the aircraft at sea level on a perfectly standard day and disregard any kind of limitations in the POH, if I just turned it on and rolled the throttle on all the way until it stopped, the engine is screaming bloody murder and the tacks are well above the green arc, the engine is going to be producing 180 brake horsepower. Another name for that is 100% volumetric efficiency. Okay. Now, as we go up in altitude, as you can see over here, you're going to lose a set amount of horsepower on average as you go up. Those numbers right there should look pretty familiar. That is your 5-minute takeoff power and your MCP in an R22. This is your MCP chart. So if we look at 8,000 feet, right here, 124 corresponds to your MCP. We are at full throttle. So what that means is if I'm flying at 8,500 feet here, I am not going to be able to produce 124 brake horsepower, okay? Now, does that mean I can't fly above 8,000 feet? Absolutely not. You definitely can. It just means that you're not going to be able to produce 124 brake horsepower. So if I'm not doing anything, if I'm not doing any maneuver or flight configuration that requires me to produce 124 brake horsepower, I'm going to be perfectly fine. But the minute that I do, I need 131 or whatever the case is, I'm not going to be able to produce that, and you're now in a situation to where you could potentially get low rotor, okay? This chart is another thing that they need to know. So this tells you, okay, per a temperature, where am I going to reach full throttle and pressure altitude? So let me kind of rewind that. So if I go over here at 40 degrees, find my mouse, hits the full throttle line, goes straight down, you're going to have a full throttle limitation of about 5,000, let's just say 700 feet, okay? This chart's also used to find your 5-minute takeoff power. So I can draw these lines all day long, and that'll give me my corresponding altitudes here, okay? Okay, this is kind of just a recap as far as what your full throttle is and really what we want the student to know. So it's just the point at which the engine can no longer produce any more additional horsepower, not enough air for it to physically suck in through the process of combustion to make that horsepower that you're requiring it to, okay? Now your bends right here in the line, if you remember from when we were going through the different parts of the chart, if you take those bends straight over, they're going to show you roughly the same altitudes as that chart we just looked at, your 5-minute power chart, okay? So if we kind of look at this again, let's look at 40 degrees, okay, right there, we take it straight over, it's about 5,500. So if I rewind this a little bit, okay, 40 degrees, about the same, 5,500 versus 5,700, I believe we said. So on and so forth. Now these temperatures will match up if we look at them on our 5-minute, or excuse me, on our out of ground effect chart, okay? And there's your full throttle line. These are the temperatures that you would reach full throttle. Above these temperatures, per this chart, you would not be able to produce more than 131 brake horsepower. Now, one question that's going to trip students up a lot is, okay, so if I hit full throttle right here, the engine is not able to produce any more brake horsepower at that point. How is it that at the same temperature, this line is all 40 degrees, at the same temperature, I can hover all the way up here to roughly, let's take that off, 7,800 feet. Okay, well, the reason is, yes, you've hit full throttle here, but as you go from here to here, your weight is decreasing. The lower your weight, the higher you can hover, okay? So this is something that they need to have written down in their POHs on a sticky note or on the side of the page. That's something that they need to have written down so that they understand. Anything that they have written down in their POH note-wise is fair game. On a stage check, they can use it. I don't have a problem with it. They just need to know how to explain it. Okay, there's a little note as far as why we can hover beyond our limitation for full throttle.